Hi, hello, good afternoon. My name is Nassim Mosavshkirvad, and I'm currently performing a presentation on Chapter 12 entitled Backtesting through Cross-Validation. This is from the book by Lopez, Prado, entitled Advances in Financial Machine Learning, edition 2018. This particular presentation is to be performed in regards to the course of Financial Data Science from Nova Information Management School. So, before we go into the chapter, I wanted to talk about a little bit about the author. So, Lopez Prado. I took this information here directly from LinkedIn, just a brief little presentation slide here, because I wanted to show that you could see that he has a total of 20 years in a corporate background, you could say, regarding data analysis and quantitative research and even machine learning. And so you can see that he has a very practical and empirical approach to his methods, you could say. Now, of course, he does have the academic background to back it up. His highest achievement in the background, or his most recent, is his postdoctoral program in Harvard, performed, if I'm not mistaken, about 2 years ago. And so you could see that that not only he has been enhancing his academic skills, he also has always been kind of the bridge in between actual corporate data and the connection to the academic research that is performed. As you can see, all of his positions has almost always been as a quantitative researcher. So, and even now, he's the global head of the Quantitative and Research and Development Division from Abu Dhabi Investment Authority. So you can see that not only has been shifting around all these places, he really has experience in a lot of types of data and really in the future. And in the future of data science, you could say. So this particular chapter is about backtesting. So what is backtesting? So the definition of backtesting is usually the method used to perceive how well a strategy would have performed and how well it would have done, what kind of forecast and output it would have regarding a specific period in the past, you could say. So it often tries to understand how would this strategy play out in a specific point in time. And if it actually performs well, then traders and analysts can have an idea of how the strategy functions and how it could be used to implement forward. And can also see what type of relations it has to different points in time and different behaviors. And so it could allow us to also monitor this decision a little bit better towards the future and potential patterns, you could say. So the applications of this are a lot, often used mostly for trading strategies, but also as a form of education and studying of certain behaviors of the market. It could be used for predictions of prices, and it also is used for validation and improvement of decision making. Like I said, it's a good tool to assess if a particular trading strategy could be indicated for this particular time frame, you could say. So usually the method most commonly used is called the walk-forward method. This method has, about this amount of advantages and disadvantages in them. So usually a good example of the walk-forward method would be, let's say, for example, you're testing a data sample from 2005 to 2006, and you obtain, for example, your best trading strategy, which is measured by your highest Sharpe ratio in that particular time frame. You would then want to see how it actually is performing that particular strategy into the next 2 years, so 2008 and 2009. So if you do that, you will have what is called the walk-forward method, where you define a particular strategy in a point and see how it functions from a particular period going forward. And that's why it's called a walk-forward. And this is particularly good because it does have a clear historical interpretation. You can understand exactly how it functions. If I were to start doing something in the market right now, how it would fare, so on and so forth. And so because of this, when using testing and training sets, you have a very little possibility of leakage in between these two, because you're defining them as points in time of particular sequential data. And so usually the main disadvantages that come with this are mostly adequate to the entire backtesting problem, which is you're still testing a single scenario that was performed in that particular training set. And so you're very prone to using a model that overfits for that particular scenario. And so you could also argue that by using this sequence of time, you could say that the data that is in 2007, 2008 has some sort of bias in it that is influenced by somehow by 2005 and 2006. So you could say the variables are kind of like, they have a relation to those values. And because you're doing this, and there is this clear connection, you could say there could be some bias in the strategies that we're using. And decisions, are often taken on a portion of the sample. You're only analyzing 2005, 2016, or even lower than that. And so amounts of sample. And so you could say that indeed you could be overfitting, or at least creating a decision that's very particular for that point in time. So it could not be applicable to many other time periods. And so, it's this need of having a balance in between necessary data and overfitting that really becomes the issue of backtesting. This seems to be, a problem occurred often in using the backtesting model, depending on the method itself. And so the walk-forward method really is the most generally common method. Because of its clear historical interpretation, it allows us to understand particular relations in between variables and how things could work. So it's a good method to understand the market, but there is some disadvantages in actually making decisions and relying on this. So the other method often used to combat a little bit of the disadvantages of the walk-forward method is the cross-validation method. So this method, let me put it in an example similar to what we were doing. This method would be, for example, if you're devising a strategy from 2016 to 2017, so you're using 2 years of data, and you devise a particular strategy that once again maximizes the highest Sharpe ratio, right? So it creates, a strategy that has the highest Sharpe ratio for that particular time. If you decide to see how would this strategy fare, for example, in the 2008 crisis, or even the dot-com bubble in the 2000s, you can see that this strategy could be facing particular stress tests, right? So if it's facing particular stress tests, you could say that, you're kind of seeing how this would fare, but it doesn't mean anything regarding the historical events. So what I'm trying to say is, there is no clear historical interpretation of this. It just gives you a notion of idea of how it performs in these particular crashes of data that occurred. And so it just gives you a notion of idea of how it functions, of what might occur in the future if a similar scenario would appear, right? So, it's less commonly used because of that. Because it's just a way of stress testing, really. And it doesn't really tell you anything of how it performed or why, okay? So the main advantage is that decisions are made on sets of equal size. So usually there is a way of creating different decisions and different types of sets. So you could use 2006 to 2017, or you could use, 98 to 99 and see how they both performed in the 2008 crash. So that usually is good because of comparability. So that could be a pretty interesting idea to try. And usually every observation is still part of a single set. So you tend to not have as much bias, or you tend to have not as much bias because you do not have the sequentiality of it. So you tend to say that these are often not correlated periods with one another because you tend to use, specific points of data to a specific other point of data. So once again, you nullify a little bit the sequentiality, which has good things and bad things. One of the bad things of not having sequentiality is that leakage can occur. So if you're testing very close data sets between one another, because there is no trailing and it can be data that sometimes is not directly, it's not time data directly connected to one another, then you could say that you could be creating testing in data sets that could overlap with each other. And so because of this, leakage can occur, which is a serious issue because it tends to overfit your model a bit. So once again, the balance in between necessary and overfitting tends to be the main concern here. So what the author proposes is a third method, a method that combines both in a certain way, which is entitled the combinatorial burst cross-validation method. So this method, enhances on the thing that usually is the big disadvantage in between the WF and the CV methods, and that is the fact that they usually test a single path. So what this often does is it tries to understand in that particular data set, for example, those 2 years that I mentioned, what type of ways can you divide data in between training and testing sets that are of reasonable size and they actually can be compared to each other, and what type of strategies could be arise from one another. And because of that, you could have like a very large amount of paths in between that particular point, and some of them, because they have some training sets and testing sets that could be overlapping with each other, there could be a problem regarding the leakage of this data set. So usually what this does after is it compares the data sets and what particular data sets are associated to each path and tries to not associate those data sets to more than one path. And so you could have various combinations of data sets, training and testing data sets, but it tries to keep the paths almost unique to each training and testing data set so that no leakage may occur. And this limits the number of paths per set of samples that we have. And so you can see, for example, that you are limited in the amount of forecasts that you can have for each path. And then you can see in this table that I extracted from the book itself, where you have from S1 to S15, you have a bunch of training of sample sets, could be also training or testing sets, and then on G1 to G6 you have observations. And so you could say that you also limit the amount of observations per each training set so that they don't overlap each other. And this means that the paths are not going to be as correlated to one another as they might seem. And so usually this can be performed by these steps here. Now I'm not going to go into these steps mostly because this is very technical stuff, and I just decided to put it here because of the people who want to try and understand how it could be done. It gives a very brief synthesis to it, but it can be very very complex, so I advise you to check the source material because it's much more explained in depth. Each one of these variables is very well categorized and explained, and even shows you how the actual variance is limited and how the correlation is actually lower than the other previous two models, and it's limited because of the number of paths. So usually the best thing about this model is it tends to address the backtest overfitting issue in a very interesting way. Mostly because first you're testing multiple methods, and you're using various types of data, various types of sample subsets, and so you're technically trying to understand what does particular strategy do across a multiple training and testing sample sets. You can see a lot of paths in between these strategy, which gives you a sort of distribution of the forecast, like I said, which tends to be normally distributed. And so you can try and understand what is the volatilities, you could say, or at least what potential outcomes and what is their difference in between all these paths to a particular outcome. And that could give you a better understanding of what an actual strategy might incur, because sometimes it's not just a singular path. And so this tends to be quite good because it uses a higher amount of observations, which lowers variance. It tends to not focus on a single path, which reduces variance, and once again avoids overfitting. And the most important of it all is that it limits the amount of paths for correlation. And so this often would say that, for example, in the case that we were mentioning of the Sharpe ratio, usually there could be high Sharpe ratios due to these problems of leakage and overfitting, and using a single path of observation. Well, this tends to be very minimized when you're using this method. And so the main key takeaway of this is that backtesting, yes, it is a very good method. It's an extremely hard method to get well and to get good results that are reliable with it. But using the CPCV method, you could also interpret a lot of other works performed with the backtesting and understand if they are incurring any errors or no. So I say for me, the main key takeaway of this is that you're trying to reduce misinformation as much as you can because you're testing it in a much more reliable way that instead of giving you a simple forecast, it gives you a variety of them. And by testing the distribution of forecasts, you have a better clue of how the actual strategy performs in all of these data sets. And of course, there are simple, backtest issues relating to data that you always need to be careful, but this actually minimizes a little bit of it because it doesn't focus on one single particular solution. And if that's the only key takeaway you would get from this, it would already be quite good. So I advise you to check I advise anyone really to check the source material. It's a fairly small chapter, and to try it out. There's examples in there and exercises. Just follow the source material as much as you can. So thank you very much for your understanding, and have a very nice evening.